Physical science, you're back. Glad you're here. All right, today we're going to be talking about is module 11-1. We have left chemistry, and now we're going to start talking about the second half of our class, which is actually dealing with the very beginning introductions to physics. Okay? And a good place. First thing I want to explain to you exactly what physics is. In my mind, I'm sure there's better definitions out there in the world in books and dictionaries, but in my mind, it always boils down to the same thing. What you're trying to observe is energy, okay? Physics seems to be the study of energy and looking at it in all of its different forms. The motion of objects, how a battery in your cell phone stores energy, how a rubber band, when you get ready to snap it across the room, the energy that is stored in that rubber band to when you release it and then it goes shooting across the room in motion. There is motion and energy stored everywhere, even in light. These fluorescent lights in here, that is a form of energy that comes down in waves. Okay, and so what we're going to do is there's like thousands of different topics in physics to talk about, and we're just going to pick like about 5 or 6 in this class, in this part, the second half of this part of this course, and we're going to start off with is motion. Okay, now before we can talk about energy in motion, which most of you learned back in middle school or elementary school, you learned about kinetic and potential energy. And that's all talking about whether energy is actually stored in something like potential energy, or whether it's kinetic energy, and that's energy that you actually see. It's in motion. Anything that's in motion has always got kinetic energy. It may also have potential, but it definitely has kinetic because it's in motion. Now, before we can talk about all that, we got to talk about motion. Now, you wouldn't think, most of us can sit there and we can look at this thing and just say, okay, there's an X with a circle around it. Is that X moving? Now, I need you to think about it for a minute. Just think about it. Take a few seconds and really think about it. Is that X in the circle, is it moving? How many of you said yes? How many of you said no? And all of you have probably a good explanation of why you think it is moving or why you think it's not moving. And you know what? All of you are right. Okay? Now, those of you who are sitting there going, hey, I'm looking at that X, brother, it ain't moving, okay? The thing is not moving. What kind of insane person would think that that thing's moving? Well, it's not insane at all, okay? If you looked at the beginning of this module, and I asked you, how would you describe the motion of the Earth? You know, most of us think about it like, some people might have thought, well, the Earth is going around the sun, right? And then we thought about, well, the Earth is actually also spinning on its axle, right? And then we're thinking about, well, okay, so that's the Earth's going around this way and it's spinning going around this way. It's pretty complex, okay? So in reality, this X in the circle right here is definitely on planet Earth. That's where I am right now, okay? Although that may be debatable at times. But I am here on planet Earth. And you look at this X on that board, you can look at it relative to the screen that you're looking at. You look at it and you go, no, that is not moving. Other of you are thinking outside the screen or outside the box, so to speak. You're going, yeah, but that's attached to the wall, the board. And this board right here is attached to the Earth. And the Earth is spinning around in circles like crazy, okay? And then the Earth is also going around the outside of the sun, okay? Another crazy thing. So our Earth is rotating around once every 24 hours, and then it takes us an entire year, 365 days to get all the way around the sun. Okay, so that is a lot of motion this thing's actually going through. So how in the world, going back to our original question, how can you describe the motion of an object when sometimes the same exact object, one person thinks of it as being still or stationary, and another person sees this complex circular motion of orbits and everything going around? Well, it comes down to being very careful how we define motion, in that you have to determine a point of reference, okay? Some of you looking at this on the board, and you're saying, no, it's not moving. And if I asked you why, how can you prove to me that this is not moving? You say, well, look at, compared to maybe the end of that line right there. You know, this length from here to here is not changing at all. Okay? It's not even rotating around over here. It's relative to this point right here, it's not moving. I'm sorry, what? Relative to that point. So if we looked at this point right here, from here to here, it's not changing. So we would say it's not moving. Now, if I took that point and I put it on the sun somewhere, now is the length between that point on the sun and that point right there, is it moving and changing? Well, yeah, constantly. Very complex, weird, circular, whipping, crazy thing going on, okay? So it all depends on relative. Relative to what? Okay, so we have to always, this little point right here is so important. Oh my gosh. Okay, most of you know who Einstein is. And some of you may know that one of his theories is called the theory of relativity. Against the word relative, right? Relative. Relative to what? Is this thing moving or isn't it? Well, it's all relative. Relative to what? Relative to what you're looking at. And the very premise, I mean, most of us think of Einstein as being some genius. And one of the most mind-boggling concepts of his time is his theory of relativity. And it turns out the whole basis of the theory stems from the simplest idea of, like, where did you put your point of reference? Einstein starts with the idea of having a rocket. And one of the points of reference, instead of this being an X in a circle, he's talking about having a spaceship. Okay? Having a spaceship. And over here, he's talking about the motion of this object relative to some, what we would call a fixed point. And then he said, I want to take that point of reference and put it on the rocket ship. And now I want you to describe the motion of the object. Well, you can tell you it's going to change. It's just like us taking that point of reference and putting it here on the board versus us putting that up there on the sun somewhere. Okay? But anyways, the very basis of his very mind-boggling concept there about relativity all depends on that very simple concept. So, the most important thing we must have to start with is called the point of reference. It's the place that you measure from. In other words, if you're checking the location or the motion of an object, you're going to have to measure it from something. And preferably you want something that is what you would call not moving. Okay? If you're going to go to build a house and you need to set the four corners where the foundation was going to be, you would be measuring from some point on the ground, okay? It would do you absolutely no good at all if that point kept on moving around, because then the four corners of your building would be all over the place, right? So preferably it's something that's not moving, like a tree, a boulder, okay? Something, stakes driven way down into the ground, somewhere that is not going to move, okay? That's what we want our point of reference to be. And then, very similar to what you just saw inside your screen on the Zoom screen there, or on your video screen, excuse me. Got too much zoom going on in my head here. Relative to the screen right here, we have to have a control of the environment. In other words, when we talk about putting this point of reference right here on the board, we're going to look at just this world here, just the board. We're going to ignore the motion of the Earth. We're going to ignore the motion of the Earth around the sun. We're going to ignore the motion of the sun because the sun's not in a fixed place. We found out it's actually sailing around, of course, the galaxy and flying off, dragging all those planets with it. So we have to be careful not only just where to put the point of reference, but the environment around the point of reference. And that is called your frame of reference. Okay? So your point of reference is where you're going to measure from, The frame of reference makes sure that your little world that you're going to be measuring and studying your moving object, that it doesn't change. Okay, it doesn't change. So we're going to kind of frame in this thing. Now, the next thing we want to talk about is, all right, we've got our little, let's use one of these little things here. Got a nice little round magnet right there. And we'll put a little X right there in the middle. Okay? And we'll have our point of reference. There's our point of reference right there. And next thing we know, it's over here. Has the magnet moved? Yes. Now, okay, that's really obvious. Okay, most of us can look at that and go, yes, I can tell it's moving, duh, okay? But we have to now use physics terms to try and describe how that object is moving, okay? So in other words, I could say, well, how do you know that thing is actually moving? You're not allowed to say, because I saw it move. No, you can't say that. That's a no-no. What's changing? And of course, if you go back to what we talked about a couple minutes ago, that distance or that length from here to here, that length right there, now it's from here to there. So it's changing. And because that length is changing, then we can say that the object is actually moving. Okay? Now, another good example to look at, because we're going to compare two words. Something called distance, which I think most of you know what it is, and a new physics term you may have heard of, but you never really studied very much. And that's called displacement. In other words, if you move an object, it's moved some sort of distance. But also if you've moved an object, it has been, some people would say, it's been displaced. Okay, if you don't know where it went, then we'd say, well, it got misplaced. Okay, a little joke there. Okay, so a good way to show you an example of the difference between distance and displacement is we're going to look at a little ladybug. Okay, here we go. We got a little ladybug here. Got the little legs on the outside. Little antennas around there. Okay, there's our little ladybug. And ladybug, especially if this is fall time, we're getting cool weather. Ladybugs are looking for somewhere to hibernate for the winter. So they go crawling around all over the place, you know, and they're just going around in circles. Oh, look at this over there. Woo! Look at that. Oh, yeah, over there. Woo! Maybe over here would be a good place to hide. I don't know. Maybe I'll go. And then our little ladybug winds up ending right here for a little while. Right there. Now, distance. Distance is the length of the entire, it's the length of that entire path. Woo! Almost couldn't get it out of there. Okay? So distance, you'd have to take a meter stick or ruler, and very carefully, because this is curving all over the place, you'd have to kind of try and kind of measure this and get this, try and get this full length of this thing all the way around the circle here, going around there, you know, here and down there, you go down to there. Then we start over again over here and go about there. Okay, so if you measured the length of that entire long pathway, probably with a tape measure instead of a ruler, then that would be your distance. Now, displacement doesn't care about which path you took. It only cares about two things. Number one, where did you start? Okay? And our ladybug started right here. Where did the second thing, where did the ladybug end? Right there. I didn't kill the ladybug, okay? Just don't want to get you upset. I just need to draw an X right there, okay? So it went from here to there. Displacement doesn't care about this big, long, curly, Q, funky little path, okay? It does not care. The only thing it wants to know is where you started, where you ended, and then you draw a straight line. And there is a direction to this, so be careful. It's from where you started to where you ended. like that. That is displacement. Okay? So distance is the length of that entire path, curly cube swirling all over the place, and displacement is short and sweet, to the point. Okay? It always goes from where you started to where you ended. It's always a straight line. Now both of these are going to get measured, and in our class we're going to be measuring distance in meters. Unless we're talking about really long distances like between cities, then we could use kilometers. That's like close to a mile long. Same thing goes with displacement. It's a length, and we're going to be using meters and kilometers. Okay? So distance and displacement. So let's go over a couple examples, and that will be it for today. I just want to go over some simple examples with you. Of course, some simple concepts here. Very important concepts though, remember? That'd be a great bonus question on your test. What phenomenal basis did Einstein's theory of relativity based on? Point of reference. All depends on where you stick your point of reference. So, here we go. We got a story. Your worksheet is a lot like this problem. So let's say, here's Bob's house. Hey Bob. Okay? There's Bob's house. Now, it's one thing I've learned about good country folks is, our good country high school students, is they go to school, and after school, as long as you don't got any chores, y'all like to go out and hang around in the woods, or out in the field goofing around somewhere. Just go somewhere to kind of goof off, blow off a little bit of steam, right? So, let's say from Bob's house to the school is 1,800 meters. And from Bob's house to the woods, where he likes to go riding his four-wheeler around on the trail, it's not too terribly far away. Let's say it's only about 500 meters away from his house. Kind of like on the back 40 or something, you know? Okay? So, question part A. Bob goes to school from home. And then rides his four-wheeler in the woods. Okay, there's a simple scenario. Bob's gonna leave his house, go to the school, and after school, gonna go back past his house, go out into the back 40 there, and go right around on this four-wheeler. So, question part, I'll just make this. Question part A here is, what is Bob's distance? What total distance did Bob travel? What is Bob's total distance? Now remember, if this was that ladybug, we'd have to take our little measuring ruler out. We'd have to measure the length of that entire path. So we have to measure the length of the entire path. So let's diagram that real quick. Make sure we understand. That means Bob here started here at his house. He went to school, right? Then he left school and went over here to goof around in the woods. Okay? So there's the entire length of the path that Bob traveled. That's a diagram. So now what we gotta do is we gotta add that total distance up. So distance is gonna be, see, from here to here is what? 1,800 meters. And then we're going to go back, right? He goes back this way. That's another 1,800 meters, right? Plus he travels that last little bit to the back 40 there, 500 meters. So that's another 500 meters there. So we have to add the total length of the entire path. So let's see here. Let's get our calculator out. 1,800 plus 1,800 plus 500. 4,100 meters. 4,100 meters. Don't forget to always put the units on the end here, okay? So 4,100 meters is the total distance, okay? Again, it's the length of the entire path traveled. Now, let's find the displacement, okay? The displacement. I should really use a different color. So I already drew the path in red, so let's do something else. Area. Displacement. What is Bob's displacement? Remember, there's only two things that Bob's really interested in, or displacement is actually interested in, not Bob. The only thing Bob's probably interested in is goofing around in the woods, or his girlfriend, probably, really. All right. But displacement only cares about two things. Where did Bob start? Bob started right here, right? Bob started right there. And after this whole day, where did Bob end? Over here in the woods, right there. You draw a line from where he started to where he ended. Now, how long is that from here to here? 500 meters. Okay, so 500 meters would be his displacement, okay? And if you really want to be technical about it, since this is actually an arrow, displacement always goes from one place to another. There's not multiple directions involved. They like us to say 500 meters to the left.